Cool. Okay, so today I'm going to talk about, I guess, results around the convergence of SGLD, and I guess to foreshadow, I guess, what we're going to talk about in this talk is it's not looking good for singular models, at least the state of the theory on this. So we're going to start out by talking about the continuous time, I guess the continuous time version of SGLD, or this continuous time stochastic differential equation called the Langevin diffusion. And then we're going to talk about discretizations of that Langevin diffusion, one of which being SGLD. Okay, so throughout we're going to be talking about a probability distribution pi, and basically in the cases that we're interested in for doing local learning coefficient estimation, pi is going to be the tempered posterior, so this thing here. None of the methods that we're actually looking at today are particularly sensitive to the form of, to pi being of this particular form. And the Langevin diffusion is defined like so. So it's a stochastic differential equation like this, where the update to the stochastic process x is given by updating along the gradient of log pi plus this additional Brownian motion term. I kind of don't want to get into the weeds of like what it means for a stochastic process to be a solution to a stochastic differential equation. So I hope it's sort of intuitively clear what we might mean by this. And I've got some links in the notes if you're looking for more information on that. Okay, so we'll let x of t be a solution, and x of t is an example of what we would call a time homogeneous Ito diffusion. In particular, it's a Markov process. And the next couple of results we can kind of state in general for general Markov processes. So I think it's useful to keep it a little bit more general here. So for any Markov process x of t, we can define a family of probability measures, which we're going to call like so. And this is going to be defined as the probability that the process at time t is in the set A, or has the event A has occurred, given that it started at x. Okay, and these family of probability measures define the distribution of x at a given time t, starting at any initial position. So what we're working towards here is basically saying what this stochastic differential equation, what this distribution evolves towards, and the right way of like as t goes to infinity, what sort of distribution does this stochastic process to converge to? And the right way of kind of framing that is this idea of a stationary distribution. So a stationary distribution of a Markov process is a probability measure nu, which satisfies the following. Oops, I'll just write it like this. for all measurable sets A and T greater than 0. So basically what this is saying is that if we start distributed according to the stationary measure mu, then that distribution doesn't evolve over time, or like the distribution of the chain stays. What am I trying to say? The distribution of x of t at time t remains as nu. Okay, any questions about that or anything so far? Cool. Okay. So the first theorem is if we suppose that pi log of x is continuously differentiable, and there exist m, a, and b in R, such that this inequality holds. Then a solution to this langevin SDE satisfies the following. So it's non-explosive. By this we mean it just doesn't reach infinity in finite time. And I'll just say has other nice but technical properties. And more importantly, 2 has pi as its stationary distribution. And importantly, that the distributions, these family of distributions actually converge to pi as t goes to infinity. This should be for all starting points x, where this thing here is total variation norm. So the supremum of over all measurable sets A of this thing. Oops. Okay, so this is like a really nice result. It basically says that, like, with some pretty mild conditions on our distribution that are sort of related to, like, I guess, like the gradient not really pushing you off to infinity, that you always get pi as the stationary distribution, and the process actually converges to that stationary distribution. And this is basically this is, from what I gather, the result that kind of people observed and thought, well, maybe we can use this idea for sampling. So this result, it's probably, I don't think it would be attributable to this paper, but it's stated and proved quite clearly in the following paper. So in Roberts and Tweedy, I think it's 1996, and that's called langevin diffusion. So this is a paper we'll talk about a little bit more. But yeah, this is like initially you look at this and you're like, oh great, well SGLD is going to work really well. Cool. Any questions about this result before we move on to the next little bit, or comments? Cool. I think I'm going to just skip straight on and start talking about section 2, so discretizations of Langevin dynamics. I've kind of got like a bit of extended aside here talking about the generators of a Markov process. And I think that's a really important topic for like actually, like I think the properties of the generator of a Markov process, which is defined in that section, are like, it's basically is the thing you need to know about to prove anything about these diffusions and also the discrete approximations. But we're not actually doing any proofs that involve it today. And I think I'd rather state the sort of main negative results that we have. And if we've got time, we can go back and talk about that. But it's also in the notes. So now we're going to move on and talk about discretization. Okay, so discretizing the Langevin equation is basically where it all starts to go wrong. So the obvious thing to do is to do the following. So if we have, I'll write down these sort of recursive update rules. So basically just taking a fixed step size and here nk IID normal. And this was suggested some time ago for simulating physical systems, and since the Roberts and Tweedy paper is known now as the unadjusted Langevin algorithm, or ULA. And it's really very similar to SGLD, except that we assume that we have access to the true gradient of the loss function, or of log pi, rather than just some estimator of it. Now in the Roberts and Tweedy paper, they go through, so that paper is I think the first paper to really get into the details of the Mahler, so the metropolis adjusted Langevin algorithm for sampling. And throughout they're comparing this to the properties of the ULA algorithm, and basically showing that the ULA algorithm has a bunch of problems. So the ULA can fail, basically. Basically due to the tails of pi of x. So in Roberts and Tweedy, they organized their analysis of ULA around the following limits, which may or may not exist. So we define S plus of A to be this.
I didn't really understand when I read this, like x is just one-dimensional here, or what do you mean by this limit otherwise?
Yes, in 1D, I guess. So yes, they only discuss this failure mode in one dimension. And I can't remember what they say about higher dimensions. I think they might say something like, well, it doesn't really work very well.
Yeah, it's probably worse.
Like, why are we going to keep on analyzing it?
Yeah.
So for now, let X be in R. We'll keep using the gradient notation though, well, I guess that's how my notes are written. And we'll define this limit. And we'll write down, I guess, a subset of their theorem 2.1 as follows. So let K be a compact neighborhood of 0. Then the number of times that xk visits k is finite with positive probability if either of the following conditions hold. So the first is that for some a greater than 1, we have that SA plus is less than 0 and SA minus is greater than 0, and they exist. Or we have that for A equals to 1, SA plus is less than minus 2, and SA minus is greater than 2. I'll give a sketch, which is what they give in the paper and cite the textbook they wrote.
But before you do that, so saying that it visits K with finitely many times with positive probability is basically saying something about it being badly behaved?
Like, yes, yeah, exactly. Yeah. So, like, well, I guess not necessarily
just be
given
orbiting around at some fixed distance or something, but
yeah, but we're going to apply this to I guess there's no particular reason that we said neighborhood of the origin here, and then in example 5, we're going to consider a distribution where like you can, like it's centered on the origin. So that will be bad for this particular. Yeah. But I think this is just generally bad, right? Like if you are taking like arbitrarily long chains and you've got like a continuous distribution, an absolutely continuous distribution, and you've got an open set that it's only visiting a finite number of times, and the probability of that set is positive, then it really should be visiting that.
Yeah, okay. Well, that's a good way of putting it, yes.
Yeah. I've avoided using the correct term here. The correct term here is that the chain is transient, which is...
Can you also take k to be increasing in size? Like it says neighborhood. Does it have to be kind of small, or can it just be like
No, by
compact
neighborhood here, I mean a connected compact set that contains an open set. So it can be really large.
So you could just keep pushing x out. So it can't be just orbiting.
Well, for a given fixed k, it could be, but yes,
yeah, that's right.
Yeah.
Wait, no, for a given k, if you read this theorem like once, then it could be orbiting. But then you could apply the theorem again to a larger k and say that its orbit has to kind of spiral outward, with maybe like a different probability each time or something like that.
Yeah, there's this. Yeah.
Yeah, I mean, it holds of any k. I guess it could be that like you grow k larger and larger, and this probability tends to 0.
Yeah, that makes sense.
I should also say I'm being a bit cautious when I say positive probability. I haven't had the time to actually read their like 500-page textbook where this proof is discussed in full detail. I think there's a good chance it is actually almost surely that this happens because what we'll see is that like a chain satisfying this property, once it gets far enough away from the origin, it sort of starts oscillating back and forth to greater and greater extreme values. So whether or not it fails is basically a matter of whether it gets far enough away from the origin. And I'm pretty sure that because this SDE is being, or the discrete time process is being driven by a Brownian motion, it'll get there eventually. But at least as stated, they just say transient, which I'm pretty sure means with positive probability rather than almost surely. Yeah.
I don't really get why SA plus being negative sort of suggests that. So the gradient of log pi x is what appears in the Langevin diffusion. And that should be negative if you want to go back towards the origin. So this being negative, doesn't, I can see why it might be 0 or not 0, depending on the magnitude of that relative to x to the a, which you're dividing by. But I think I don't really have a good intuition for what SA plus is measuring and why negative would be something that I would... Maybe the proof is going to show me.
Yeah. Well, let's look at the proof.
Yeah.
But yeah, basically, it's not that it will get pushed away from the origin; it's that it will significantly overshoot the origin.
Oh, okay, that makes sense. I got it. Yep.
Okay, so this is a sketch. Suppose x is large, so that s plus a is approximately equal to its limit. Right, what am I trying to... this is just true by definition. What I mean to write is this. So if we'll talk about the A equals 1 case. The next, x prime is approximately okay. So if we have that SA plus is less than -2, then we have that x prime is less than negative x. And the problem with this is that the same thing holds true of the next step. If we replace SA plus by SA minus, and we get that XA prime prime is again, I guess, is greater. Hang on. Do I have? These the right way around. Okay, this should be positive. Yes, sorry, this is correct. Yeah. Then we get the next position after that will again be greater than the previous in magnitude than the greater position. And basically we just get this oscillation between increasingly extreme values of x. There's a similar argument for a greater than 0, and they give they reference a more sort of rigorous proof of this in their paper. I think that the argument, they don't really touch on it, but I think the argument that like eventually you get to a sufficiently large value of x basically follows from the fact that Brownian motion is ergodic. So eventually you're gonna get out there. Yeah.
Yeah, it makes a lot of sense why this would be a problem for singular distributions. I mean, it's basically because of the soft mode, right? You take big steps.
The soft mode?
I'll make a comment on this when you give example 5.
Cool. Okay. But yeah, there's lots of examples in Roberts and Tweedy, which is really, really nice, including cases where the SGLD chain converges, but to a different distribution, which is a little bit sort of like evil. I don't know how contrived that one is. It's like quite a strange, it involves setting the step size kind of like unreasonably large. But yeah, they talk a lot about this. And all their sort of toy examples are sort of systems driven by polynomial potentials, which is like really nice for like us, because they're filled with singularities and things.
Curse the mathematicians! Why do they have to come along and ruin it?
Yeah. Cool. Okay, so now we'll talk about example 5 here. So if we have pi proportional to this thing, I guess here these are the like obvious things, right? And what this means is that the gradient of log pi is equal to -2 gamma b x to the 2b minus 1. And then we have that the limit SA plus is equal to the following. Okay, and then basically we note.
Sorry, just
that
going back to the
plus-
sketch. So x prime is approximately x plus SA plus, and that's just basically ignoring the injected noise, right?
Yeah, I also had this question. I basically ran out of time to look at this in detail before the talk. I'm not sure what their argument is for ignoring noise. I guess the way, actually, I didn't quite present this how I wrote it in the notes. I said the expected next position is approximately what it is. So I guess in expectation, this is true. But I think it does require like a more careful argument.
Okay, that probably factors into this, the final sentence, but otherwise seems okay, yeah.
Yeah. Cool. So here we have that the SA plus limit is less than 0 if and only if 2b minus 1 minus a is equal to 0. So if...
Oh, there's a typo in your note, by the way. You wrote x prime is approximately x plus SA plus, but what you mean is x SA plus.
X prime is approximately x plus...
Because it...
Oh, yeah. There's that extra factor of...
Yeah.
Cool.
But then this quantity makes a lot of sense because it's like basically what happens if you try and turn the update into a multiplicative thing.
Yeah. Yes, that is true. Cool. So what was I saying? Yeah, so in example 5, basically if the power of x in this equation here is 4 or more, then ULA fails to converge. So this is like kind of bad for makes you kind of nervous about what SGLD is going to be doing. At least it makes me nervous about what SGLD is going to be doing.
Oh, dear, yes.
I think it's interesting in that they come from directly being, this error doesn't directly get generated by like the degenerate critical point, but it happens because these distributions have lighter than Gaussian tails.
I would say, I think that makes sense in the sense that like it's not directly, but so to come back to the comment about soft modes. So a soft mode is in physics what happens when you have like a mode. So from our point of view, that would be some quadratic term in a potential. If the coefficient, that is the eigenvalue of the Hessian, goes to 0, then that's called a soft mode, and it's soft. Like literally, if you study like the lattices and crystals, when a mode becomes soft, it means the material is literally soft. So like a perturbation, it doesn't have any restoring force, right? It's not rigid, it's soft. And so the mathematical cause of that is that some eigenvalue goes to near 0, which means that the restoring force is sort of extremely weak. But what that means in terms of, the quantity that we're looking at here, it's exactly the same as why this is large. So why this? Oh, okay, maybe I take that back. No, I think that is right. Yeah, I mean, it's the same phenomena. I guess one doesn't. Okay, I'm a bit confused. Sorry, I might come back to this comment.
Yeah. Yeah, I think, like, I guess there's still this sort of the question open here, at least as I see it. Like, after looking at this example, you're like, okay, like, if there's degenerate, like, is it possible to have degenerate critical points, but tails that are more like a Gaussian? And I guess I don't know. I haven't thought about that too much, but like, we're about to see that DLNs don't don't have that property. Their tails don't look like they're lighter than Gaussian tails. So you'd expect to see this issue happening there. So there's still, even if this is true of like, a transformer or something, there's still like an open question of like, well, why does SGLD actually do anything useful in DLNs? Yeah, I think. Yeah.
I think I sort of understand why I'm confused. I mean, there's a sense in which the step you're taking here is not. So this is sort of simulating. I mean, you have a velocity basically, right? Because you're adding it to the position. So the soft modes, like, there's a lack of restoring force, right? Which means that if you any like slight perturbation, I mean, basically the physical intuition about a soft mode is that any noise. I mean, if you have a normal mode, that's kind of a stable equilibrium, right? Because any noise, there's always noise, and any noise that interacts with the system there'll be a restoring force which pushes you back towards the equilibrium, and so that's why it's stable. A soft mode, however, a system won't stay at a soft mode because any source of noise will push it in some direction, and there will be no restoring force that pushes it back. I sort of feel like, I mean, my intuition thinking about this from that point of view is something like, there's some sense in which to perform this SGL, it's like some, maybe it is the discretization, like the.
Yeah. I mean, I'm not sure I follow, because like here we get, it's almost the opposite situation. Like we have a really strong restoring force, but because it's discretized.
Yeah, but it's not a force though, right? Because the 2.1 is not about acceleration, it's about velocity. So you have to...
yeah, okay.
So the actual, like... yeah, I feel like it's more like... I'll think about it. I think it's... Yeah, I think somehow that's correct, but I have to translate it somehow.
Yeah.
It's very interesting, though. Yeah.
Yeah. And yeah, worth pointing out as well, or like it's as written on the boards, but like the langevin diffusion doesn't have this problem because of... Cool. Okay, let's talk about SGLD.
I think, sorry to keep making vague comments, but
yeah,
it's very interesting. I think it's like, it's annoying for the experimentalists, but for the theoreticians, I think it's quite exciting in a way, because it's actually giving a quantifiable connection between the entropy you need to spend to generate samples, right? Like, so maybe the discretization, I mean, there's sort of this link between the amount of information required to specify a parameter and, that's as Edmund's been presenting over the last few months, got to do with like how you discretize the space and so on. And this sort of suggests, I mean, a naive solution would be something like, maybe we should like use some different kind of discretization that's more sensitive to the degeneracy or something, right? But that would then involve like spending more cycles to perform the approximation, right? But that's actually really interesting because that's expected actually, right? Because in fact that's the kind of information theoretic root of why SGLD shouldn't work, is that actually the surprising thing is that you don't have to spend that much compute, even though the degeneracy should make it hard to sample, right? And so I find it really quite interesting that this failure is pointing maybe in a direction of like being able to quantify the connection between that failure, which is like the practical difficulty in estimating the posterior in our case, and some theoretical aspect of the complexity, which is, the sort of, if you like, the MDL kind of story. Yeah, so, and I mean, that actually connects up to the sort of jet scheme geometry and so on. It's got to do with the complexity of the, there's some deep relation between the complexity, like some notion of complexity of the trajectories, the solution trajectories, and like the geometric complexity near the point. That's sort of what Simon's been thinking about. So actually this is like going in a really interesting direction. Okay, I'll shut up now, but I'm quite entertained.
Yeah, good. Cool. Let's talk about SGLD. So there's a proof, or there's a paper that is proving that SGLD does indeed sample from the posterior, or from any distribution type. I'll just write up the name of that paper now. Where is it? They write out the full name of the algorithm in the title. Cool. But basically, this paper imposes assumptions that imply a degree of regularity of the model. So this is the setting that they consider SGLD in. So they consider I guess the two differences from like how it's normally written down is they consider just a general unbiased estimator of the gradient, which they impose assumptions on. And they consider a possibly step-dependent sequence of a sequence of step sizes rather than a fixed step size. There's some follow-up work that's sort of looking at, I guess, for a given fixed step size, if all of these conditions hold, then what do you, how close can you get to estimating accurately? But in this one where they actually show convergence, it requires a decreasing sequence of step sizes. So let's put their assumptions up on the board. The first one is what I just said. It's that the step sizes are a decreasing sequence which converges to 0, and that the sequence of partial sums of these step sizes converges to, or I guess diverges to infinity. And I guess the more interesting assumption for us is this next one.
Sorry, I don't think I need to read that, but I can't. So that's sum I equal 1 to k epsilon I, but what's the thing on the left-hand side?
Oh yeah, this is this thing that I rubbed out. This is tk. So just introducing some notation. which I think we maybe won't even use. Cool. So here we assume that pi x and g of x u jointly satisfy the following. There is a function v from d which is twice differentiable. V of x goes to infinity, oops, as the size of x grows. And importantly for us, Vx has bounded second derivatives. And it has the following properties. We're actually only going to talk about two, so I'm just going to write two on the board because they'll take a while to write up. But two is the sort of important one. It is that there exists a constant C2 such that the gradient of V of x plus the gradient of log pi of x is, there's a typo depending on when you downloaded the notes, there's a typo here, but this is what it should say for all x. And their main, before we go on and talk about what is going wrong with this, I'll just quickly write up their main theorem, or one of their main theorems, which is that the distribution you get at step k converges in distribution to pi. Oh yeah. So the distribution, the sort of finite k distribution, converges in distribution to pi almost surely. That's stated better in the notes. And they actually show some stronger stuff than this, and that's all written out in the notes as well. But let's now move on and talk about why assumption 2 is a problem for singular models. So basically, it's because of the interaction between the fact that V has to have bounded second derivatives and this condition 2 in the assumption 2 that I wrote up. So if V has bounded second derivatives, then there exists degree polynomial P of x such that V of x is bounded above by that polynomial. And yeah, this is basically where things go wrong. So what we can do is we can prove that, I'll just write this out in words. Any deep linear network satisfying assumption 2 by which I mean for a deep linear network, if it's doing regression, then the tempered posterior distribution satisfies assumption 2 necessarily has at most 2 layers. Yeah, so that's kind of, well, I guess it basically means that this theorem doesn't apply in the case of the sort of QD paper using SGLD to estimate the local learning coefficient.
So condition 2 like has some sort of similarity to 2.2 or like SA plus less than 0, but not exactly. How should I think about this failure also as being about the discretization? I mean, it could also conceivably be about the mini batching, but I guess I don't know. How do I think about what the source of the failure is?
Condition 2 here.
Yeah.
As in why a deep linear network fails to satisfy.
No, that I see, but.
Oh yeah.
So I mean, okay, the assumption failing doesn't mean that it doesn't work, but what would you derive? I mean, given what we've discussed in the previous section, I guess I sort of am willing to buy a story that points to this failure as actually suggesting that the discretization is also going to be like that not only could it fail, but it will fail. Is that how I should think?
I'm not sure. At least when I first read it, I read this and thought, like, okay, so here's how I understand this assumption. So V is basically like its job is in condition 2 is to control the tails of the gradient log of the true gradient. So condition 1 is about the estimate of the gradient, and condition 3 is about basically making sure the gradient is always pointing like roughly towards the center of the space, like the highest region of distribution concentration. The condition 2 is like a weakening of the condition that pi needs to have like tails that are like a Gaussian.
Yeah.
So it gives you more wiggle room, but it still puts too strong an assumption on it.
Yeah.
Is how I think about it.
I see.
So yeah, we've detected language that may violate our
the tails are non-Gaussian tails. That's like a swear word.
Yeah. I think, given the time, let's not talk through this proof. I mean, it's written out in detail in the notes.
Yeah, that's nice.
But actually what I do want to talk about, and maybe if we could end the recording or cut the recording off here, is like so what